So we might also be interested in what the volume is in the tank as a function of time. This is a cross-section of the tank, and this is the subdomain of the region that we were modeling. And when the mesh deforms, this square becomes a rectangle as the fluid drains out. And so we can determine the volume in the tank by measuring the area in cross-section and then just multiplying by the width of the tank. So the problem then is to determine the area, and that can be done by going over here to derive values. And if we integrate the surface of this region and we select that surface, we make the integrand 1. And so if we integrate 1 over this surface, then the result is simply the surface area over which we've integrated. And you can see that it correctly gives us the units of meters squared. And so this is a way to determine the area of the subdomain and how it changes with time. So we need to make sure to select solution 2 here. That is the data set that includes automatic remeshing. So we do that, and then I'm going to clear out the data, and we do evaluate. It does the calculations, and now we can plot it here. This is the cross-sectional area of the water in the tank as a function of time. If we multiply by the width of the tank, and this is then the volume as a function of time. And you can see it decreases, and then the rate at which it decreases kind of flattens out. Starts at 1 and it ends, it's kind of hard to tell just where it ends, but if we look at the data set, at x equals 100, y is 0.018. So it's a little bit less than 2% of the water that remains in the tank at the end. Good, that could be quite useful. One of the things we might want to do is to just check our analysis and see if this makes sense. We know that under ideal condition, vertical walled tank, when it drains by gravity, function that describes the drainage is a negative exponential function of time. We can check and see whether this is a negative exponential function by plotting it on semilog axes, and we can just change the y-axis to semilog. If this is a negative exponential, then this curve would be a straight line. And you can see that it's pretty close to being a straight line. Let's go and check it out. I'm going to copy it and paste it over, and then here's a straight line. We can see that it's really quite close to following the volume as a function of time that's predicted by our analysis. Now, it's not exactly a straight line, and that's because our tank model has the flow coming down and then converging and flowing out to the sides. Under ideal conditions, there really is no flow within the tank. It simply drains at a rate that's directly proportional to the height.